Okay, so you send over some really interesting material about pyrogen testing, basically. How manufacturers check that their products won't cause a fever. Let's dive into that.
Yeah, absolutely. It's essential stuff.
We're looking at testing for things like injectables and medical devices. And these pyrogens, they're fever causers. Your sources really zero in on bacterial endotoxins, LPS, right? From gram-negative bacteria.
That's correct. They're a major focus because even tiny, tiny amounts can cause a reaction, a really significant reaction.
Right. So safety is the big deal here. Testing is absolutely vital. We've got some articles, your notes, and the mission, I guess, is to get a clear view of why this testing happens in the main ways it's done without getting totally lost in the weeds.
Exactly. Keep it clear, keep it focused. And it's interesting for these parenteral products, things going directly into body. There have really been two main testing strategies historically.
Okay. The first one your sources mention is the rabbit pyrogen test, the RPT. What's the basic idea?
Well, the RPT tries to mirror how a human might react. You inject a sample into rabbits and you watch their temperature, see if they spike a fever.
Rabbits. Why rabbits?
They have a similar fever response to humans, historically speaking. The procedure involves picking healthy rabbits, getting a baseline temp, then an IV injection of the product sample.
And then you just wait.
Monitor their temperature closely for about 3 hours. Then you compare any change against set limits to see if it passes or fails.
So what's the upside? Why use this method?
Well, it was the original standard for a long time. And a key point is its broad range. It can pick up different kinds of pyrogens, not just the bacterial endotoxins we mentioned.
Okay, broad range, but I'm sensing a but coming. What are the downsides?
There are definitely significant ones. Obviously, there are ethical concerns about animal testing. That's a big one nowadays. But also, the results can vary from rabbit to rabbit or even test to test. Interpretation can be a bit subjective, too.
Subjective. How so?
Well, defining the exact threshold for a significant fever response wasn't always perfectly clear-cut. Plus, it's slow, takes hours. And critically, it's just not as sensitive as the alternative, and it doesn't really tell you how much pyrogen is there, just if it caused a fever.
Less sensitive, less quantitative.
Yeah.
Got it. Okay, so that leads us to the other main test, the bacterial endotoxins test, BET, often called the LAL test. Something about horseshoe crabs.
That's the one. Limulus amoebocyte lysate. It's an in vitro test done in glassware, basically. No animals involved directly in the testing step itself.
And it uses blood cells from horseshoe crabs.
Exactly, from their amoebocytes. These cells contain enzymes that react incredibly specifically with bacterial endotoxins, the LPS. This reaction causes a change we can measure.
A measurable change.
Yeah.
Like what? Your sources mentioned a few ways.
Yeah, three main methods fall under the BET-LAL umbrella. There's the gel clot test. It's qualitative, basically. If enough endotoxin is present, the mixture forms a solid gel, like Jell-O.
Okay, simple yes, no.
Pretty much. Then there's the turbidimetric test. This one is quantitative. It measures how cloudy the mixture becomes over time. More cloudiness means more endotoxin.
Ah, so you get a number.
You do. And the third is the chromogenic test. This one often boasts the highest sensitivity and is also quantitative. It uses a chemical substrate that releases color when the LAL enzymes are activated by endotoxin. More color, more endotoxin.
Brighter color equals more contamination. Makes sense. So walk me through the general process for LAL.
Sure. You prepare your sample, you reconstitute the LAL reagent, it usually comes freeze-dried, mix them together, incubate under controlled temperature and time,
Right.
and then you measure the outcome. Is there a gel? How cloudy is it? How intense is the color? You compare these results against standard curves made with known amounts of endotoxin.
And that gives you a concentration.
In
Endotoxin units, EU.
Exactly. Endotoxin units per milliliter or per device, depending on what you're testing. And then you check if that number is below the acceptable limit set for that specific product.
Okay, so the advantages seem pretty clear here compared to the rabbits.
Definitely. No animals for the test itself. Higher sensitivity, detecting really minuscule amounts. You get actual numbers. It's faster, more objective, easier to reproduce reliably. And you can even automate it.
Big pluses. But any limitations to the LAL test?
The main one is its specificity. It's designed for bacterial endotoxins. If there's a concern about other types of pyrogens, non-endotoxin pyrogens, LAL won't pick them up.
so it might miss something the rabbit test could catch.
Potentially, yes, though bacterial endotoxins are by far the most common issue. Also, sometimes things in the product itself can interfere with the LAL reaction, either inhibiting it or enhancing it.
Ah, okay.
So you have to perform what's called suitability testing or validation first
Right.
to prove the test works correctly for that specific product formulation.
Makes sense. You need to validate your method. Now, regulatory bodies, FDA, EMA, others, they mandate this testing, right? It's not optional.
Absolutely mandatory. It's a critical quality control step required by pharmacopoeias like USP in the US, EP in Europe, JP in Japan, and enforced by agencies like the FDA and EMA for parenteral drugs and medical devices.
And is there a preference, regulatory-wise?
There's definitely a strong global trend towards using betlol whenever possible. The ethical arguments, the better sensitivity for endotoxins, the quantitative results, they all favor LAL.
But the rabbit test isn't completely gone.
Not completely. In some specific situations, maybe for certain biological products, or if there's a known risk of non-endotoxin pyrogens, regulators might still require or accept the RPT, but the default is increasingly LAL.
And regardless of which test, it has to be done properly. Validated procedures, strict criteria.
Precisely. You can't release the product unless it passes these tests according to very strict predefined standards.
Okay, so wrapping this up, the big takeaway is pyrogen testing is absolutely fundamental for the safety of anything injected or implanted. The rabbit test was the old way, broad but with issues. The horseshoe crab LAL test is now largely preferred. It's super sensitive to the main culprit, bacterial endotoxins, gives actual numbers, and avoids animal use in the test itself.
That sums it up well. Safety first, and LAL is usually the best tool for the most common threat, which, leads to an interesting thought.
Go on.
Well, considering how science keeps moving, especially in understanding biology and safety, what might be next? What kind of innovations could refine these tests even further, or maybe even replace them entirely down the line? Could we see perhaps cell-based assays using human immune cells, or maybe advanced chemical detection methods?
Yeah. Moving beyond even the horseshoe crab. Fascinating possibility. Definitely something to chew on.
Yeah.
Well, thanks for walking us through all that. Really appreciate you sharing the sources and breaking down this crucial testing process.
My pleasure. It's important stuff.